wrapping up 4.6. So we had talked about finding zeros. When I said complex zeros, that wasn't any different than 4.5. Sorry about that. It wasn't any different than 4.5. It was just that we sometimes get to a place where we get some complex roots, some stuff with I. So 2 is still a complex zero, but 2 plus and minus I is also. If you look back at our examples that we did, the two examples that we did for finding complex zeros, you'll notice something about these complex numbers with the imaginary parts in them. So something that I skipped over before we started was this fact that when you have a complex zero, a plus bi is a zero of a polynomial, then so is a minus bi. And that thing is called the complex conjugate. So if you have imaginary parts of zeros, they'll always come in a pair of twos. Complex conjugates. It's a J. So, for example, if you have a polynomial of degree 5 and negative 2i and 5 minus 3i are zeros, what are the other two? It's a degree 5, so it has to have 5 of them. Well, negative 2 doesn't have an imaginary part. I is imaginary, so it needs its conjugate. How do we get the conjugate? You take the opposite sign of the I part. So negative I also has to be a 0. And then looking at 5 minus 3i, the imaginary part minus 3i has to flip signs. So 5 plus 3i also has to be a 0. So let's do what we were doing for 4.6 backwards, where I'm going to give you zeros and then you're going to write the polynomial that has them. So let's write a polynomial that has zeros I and 4. So the first thing you would say is that, well, negative I also has to be a 0. But writing these as a polynomial can get a little tricky. We're normally really good about taking 4. Actually, you know what? Let me rewrite this. 4i and negative I. We're normally really good about 4 being able to see that it's x minus 4. You have to be able to think about it in the same way with these. So if I is a root, that means it would factor to x minus I, because if we plugged it in, we'd get 0. And the same thing here. That would be the factor x plus I. Now, we do not write, even in factored form, factors with imaginary numbers. When we're dealing with polynomials, we only want to use real numbers. So even though we can have imaginary answers, we're not done, is basically what I'm trying to say. So when you do stuff in class, you have to write it in factored form, but that factored form cannot have imaginary pieces. So the x minus 4 would be fine, but then we're going to have to multiply these two things together. X times x, x times I, minus I times x, and then negative I times I is minus I squared. You will notice that when you multiply these conjugate factors together, the middle stuff always cancels. And then I squared is negative 1. So we get our factored form of x minus 4 times x squared plus 1. Now, that might not be so bad, but what if I gave you something like, give me a sec, I gotta find the problem. what if I gave you the same kind of prompt, like give me a polynomial, factored form, that has zeros 0, -5, 7i, and 4 minus 3i. A little bit more to do here. We see 7i, we know that -7i has to be a 0 as well. We see 4 minus 3i, we know that 4 plus 3i has to be 0. So what are all of our factors? 0 just gives us x. -5 gives us x plus 5. The 7i's, 7i and -7i give us x minus 7i and x plus 7i. Now these other ones, these are the ones where people make so many mistakes. This is really challenging. People are tempted to put x plus 4 minus 3i and x plus 4 plus 3i and just have the I parts change. But we're not allowed to do that. We take these values and subtract them. So it's x minus the 0, which is why I'm adding in an extra set of parentheses. Now this can be a pain to multiply out, and I'm going to show it once. Of course, I didn't leave myself enough space, but I'm going to show it once, then I'm going to show you a shortcut on how to do this quickly. X plus 5, x squared plus 7xi minus 7xi, those will cancel, minus 7i times 7i, so that would be x squared minus 49i squared. Then I'll do this work over here. Let me simplify this. I squared is -1, so this is x squared plus 49. So I've taken care of those four. How would you have to multiply these out the long way? Well, I would distribute the negatives first. So x minus 4 plus 3i, x minus 4 minus 3i. And then here's where you have to be careful, and I'm going to grab a couple different colors here. X times x times minus 4, x times minus 3i. X squared minus 4x minus 3, I'll do ix. -4 times x, -4 times -4, -4 times -3i. So that would be minus 4x plus 16 plus 12i. Let's grab one more color. 3i times x, 3i times -4, 3i times -3i. Gives us plus 3ix minus 12i minus 9i squared. This takes a while, and one little tiny mistake makes the whole thing go kaput. Just got to be careful, but you'll notice that we have a minus 3ix and a plus 3ix. Those will cancel. We have a plus 12i and a minus 12i. Those will cancel. And we are left with x squared minus 4x plus 16. Minus 9i squared is minus 9 times -1, so that's plus 9, giving us a grand total of x squared minus 8x plus 25. So there's the polynomial in factored form with no imaginary parts in it, with these 6 zeros. Now I'm going to show you a faster way to do this. We'll do one more example of finding zeros, and that will be that. So let's go back to this fact that x equals 4, I'll do plus or minus 3i is a 0. Now I taught this a little different in class, but I actually prefer this way, so I'm going to show you this way. How you can come up with the quadratic that gives these two values. You're going to subtract the real part over, or you're going to move this part over. So it's 4, so we're going to subtract 4 from both sides. That gives us x minus 4 equals plus or minus 3i. And how do we get rid of i's? The easiest way to do that is to square them. So if I square this side and square this side, equality still holds. I'm allowed to do this. X minus 4 squared is x squared minus 8x plus 16. Whether it's plus or minus, the squared takes care of that. so this would be 9i squared. But I squared is negative 1, so this is x squared minus 8x plus 16 equals negative 9. And we want this to be equal to 0, so we add 9 to both sides, and we get x squared minus 8x plus 25. You will notice that that is what we ended up with going the long way. So this is a shortcut. So let's do one more like this, and then I'll get to my very last example. So let's say we're going to write a polynomial that has zeros, so I'll say in factored form, with zeros. Let's do 3, negative 5, 6 plus 2i, and 4 minus I. I don't know, we'll do that. So the first thing you have to think about is if 6 plus 2i is a 0, so is 6 minus 2i. If 4 minus I is a 0, let's do actually, I'm sorry, I'm changing my mind. Let's do negative 4. If negative 4 minus I is a 0, then negative 4 plus I is a 0. The factor that would give us a 0 of 3 is x minus 3 and x plus 5. Now, how do we find the factors that give these zeros? I'll go through my method 2 more times. Well, I know x has to be equal to 6 plus or minus 2i. We're going to move the real part over. X minus 6 equals plus or minus 2i. We are going to square both sides. We get x squared minus 12x plus 36 equals 4i squared. And 4i squared is the same thing as negative 4. Adding the 4 to the other side, the factor would be x squared minus 12x plus 40. And then over here, if x equals negative 4 plus or minus I, we need to add 4 to both sides. X plus 4 equals plus or minus I. We square both sides. X squared plus 8x plus 16 equals I squared is negative 1. We get x squared plus 8x. Plus 17 when we add the 1 to the other side. So the polynomial in factored form, which I would not want you to spend the time multiplying out. It's a 6th degree polynomial that would take you forever to figure out what all of it was. Looks like this. You take this polynomial right here, you plug in any of these 6 values, and you do get 0. Okay, to wrap up 4-6, I'm going to do one more example of finding complex zeros. This one is a strictly without calculator. X to the 4th minus 15x squared minus 16 equals 0. So the reason that this one is strictly without calculator, if I tell you to do any of these without a calculator, that means you have to have a way to factor them. Since we're finding complex zeros, I see the degree is 4. I know we need 4 answers. So looking at this, I'm hoping you know how to factor this. Here's what you're thinking about. This is an even degree. This is an even degree. And this is it's not kind of. It's the same thing as writing this. This is in the form of a quadratic. You know how to factor. Something squared minus 15 times something minus 16. Which you would tell me is something minus 16 times something plus 1. And what's that something? In this case, it's x squared. So this thing factors to x squared plus 16, and then x squared, minus 16, pardon. And then x squared plus 1 equals 0. For this one, since it doesn't have the middle term, we don't have to do quadratic formula or anything. Actually, you'd know how to factor this. I don't even need to talk about that. You could factor this to x minus 4x plus 4. So you'd know 2 of our zeros are 4 and negative 4. This one, not missing it's missing the b term. So to solve it, we can just use square roots. Subtract 1 to the other side, take a square root, the square root of negative 1, plus or minus I. And there are our 4 answers.